This is part 4 of lecture 7 of LX 5300. We'll be talking about estimator bias. So when we're dealing with estimators, it's important to remember that the estimate that's generated is itself a random variable. Now to see that, let's just recap where we were. We have a distribution that we're interested in, f of x, which depends on some parameters theta. So determining this distribution here are a set of parameters theta which are unknown, but they're somehow fixed. There's nothing random about these, it's just that we don't know what they are. And so we want to try to figure out a good estimate of these from samples drawn from this distribution. So we have samples that we've drawn from the distribution x1 through xn, and this is what we've called our training data. What we do with this training data is we feed it into an estimator, and this gives us some estimate, big theta, which is trying to be hopefully close to the unknown parameter theta. But because this training data here is random, the value of this estimate is also random, and so it is a random variable. So what we like to know is, well, what are the properties of this random variable? And can we use those properties to kind of describe whether this thing coming out of the estimator is actually a good estimate of this? So the first thing we want to look at then is the idea of the bias of an estimator. So the bias of an estimator is just the difference between its expected value and the actual value that we're trying to estimate. And so what this really means is that if I was going to run this estimator many times, then each time I run the estimator, I'm probably not going to get the exact value of theta, right? Hopefully I get something close, but what this is saying is that on average, right, I should be somewhere around theta, right? In particular, the average value of all my estimates in the long term should be equal to theta. And so if it's not, right, then I say there's a bias, right? Otherwise, if the expected value of big theta is equal to theta, then I say the estimator is unbiased. Now in the previous section we saw that the maximum likelihood estimator is often the sample mean. It's not always the sample mean, but in many cases it is the sample mean. And that's nice because it turns out that the sample mean has another nice property, that it is in fact an unbiased estimator of the mean of the random variable. And this is quite easy to prove. It basically just uses the linearity of the expectation. So this here is the definition of the sample mean. I just apply expectation to the left side and the right side. I move the expected value inside using linearity of the expectation, and now I have that the expected value of all the individual data points is just the sample value, that the expected value of the distribution, since they're all drawn from the same distribution, so that's theta. And so when I sum this n times, I get n theta, and when I divide by n, these two cancel out, and I just get theta. Right? So the expected value of big theta is just theta. So the n here, the subscript n, indicates the number of data points that I am summing over. Right? And so what this says is, well, it doesn't really matter. If I sum over one data point or two data points, I'm always going to get an unbiased estimator of the sample mean. Now intuitively, that's nice, but at the same time we expect, well, isn't it going to be true that the more data points that I get, the better the estimate is going to be? And that's true, but it doesn't improve the bias. There's no bias no matter what n you have, but it does improve the variance of the estimate. And so the variance of the estimate is a measure of how close your estimate is going to be on average. And we can show that the collecting more data is good because as n increases, then the sample mean estimate is a sequence of random variables, right? So for each, let's say, piece of data, that new piece of data I can get in, I can estimate a new sample mean, and then if I have n plus 1 piece of data, I get another estimate of the sample mean. And as n gets bigger and bigger, I'm going to get closer and closer to the thing that I'm trying to estimate, the expected value in the mean square sense. Another way of saying this is that as n increases, the variance of the sample estimate, the sample mean estimate of the mean goes to 0. So for the proof of this, we note that, well, since we already proved that the expected value of the sample mean is equal to the mean of the distribution, then the difference between the estimate and the thing that we're trying to estimate, expected value of x squared, is just exactly equal to the variance, because expected value of x is the same as the expected value of the estimate itself, and this is just then the definition of the variance. Right? So this is just the definition. And here all I've done is I've substituted in the previous result that we had. Now, since this thing here is the sum of a bunch of independent random variables, then the variance of the sum should be the sum of the expected, the sum of the variances, right? And so the variance of this should be the sum of the variances of these xi's scaled by something here, and because I'm scaling the sum here by 1 over n, when I compute the variance, which is a squared statistic, I have to scale by 1 over n squared. And so now these are all the same. These are all sigma squared, and I have n of them, so I have n times sigma squared, and I divide by n squared, and I go sigma squared divided by n. And so what this is showing you is that the variance of the sample mean estimates goes to 0 as n goes to infinity, and this is also the mean square distance between the sample mean and the thing that we're trying to estimate, the mean of the distribution, and so that means that it converges in mean square. Finally, I'd just like to point out that the maximum likelihood estimate does not always lead to an unbiased estimator. We've already seen this. For example, when we looked at the uniform distribution, we noted that if we assume a uniform distribution between 0 and m, and we want to estimate the value of the m, the maximum value of the uniform distribution, the maximum likelihood estimate is just the maximum value in the data. Right? So that means that the mean, the maximum likelihood estimate of the mean, would be 1/2 the maximum value, which is not the sample mean, and we would expect that to be smaller than the actual mean, on average at least. So it turns out that a similar case holds for the maximum likelihood estimate of the variance of a Gaussian distribution. So this was the maximum likelihood estimate of the variance of a Gaussian. And if I take the expected value of that, then I can show, and I don't do that here, but it can be shown that it's equal to this, where there's this scaling factor n minus 1 divided by n times sigma squared, the thing that we're trying to estimate, and so this is actually slightly smaller. And the reason that this is slightly smaller is that what we have is we have chosen x bar here, which is the sample mean, in a way that actually minimizes the variance among all the data points. Right? And so the easiest way to see that is if we have a sample point, let's say just x1, then when we choose the mean, we're going to just choose the mean to be x1, and in that case the variance, the estimate of the variance, is just 0. Right? Alternatively, if we had two sample points x1 and x2, then we choose the maximum likelihood estimate of the mean to be the point in between them, and that's also going to result in the smallest variance in this distribution. And so this is especially significant for small values of n, right, 1 or 2, but gets less and less critical as n gets bigger and bigger, right? And in that case, n and n minus 1 don't differ by that much. For example, if we have 1,000,000 observations, it won't make that much difference. However, we can still correct for that bias by just, instead of dividing by n, we can divide by n minus 1. And so now this thing is another possible estimate of the standard deviation. It's not the maximum likelihood estimate, but it is an unbiased estimate. And so that's why sometimes in statistics textbooks you see this equation as being the estimate for the standard deviation of a distribution. Okay, so moving forward, we're going to look at next time the Kramer-Rao bound.